All right, guys, let's get going. Here we go. So today we're just simplifying some roots. Today's lesson is about graphs of roots, square roots and cube roots and things like that. Pretty straightforward. Shouldn't be too bad. Let's get this stuff over with. Here we go. We got plus or minus some root. Now the plus or minus really does nothing. It's just hanging out in front. Our real work is on the root. How do I simplify this root? Well, here we go. First off, it's an odd root. So you don't need to worry about absolute values for odd roots. Only for even roots is that really a concern. But the rest of the strategy will be the same. I'm trying to do a cubic root, so I want to find cubes, things that can be cubed that go into this. So you look up on your chart of things that are cubed, and is 54 a perfect cube? But 27 is, and 27 does go into 54 2 times. So just like with square roots, you want to find things that can go into it. So we can break this up into a 27 and a 2. What about the x's? Well, you know what the new exponent should be when you do the root? It's this divided by this. You know that? But is 7 divided by 3 pretty? Not really. So let's break this up. What divided by 3 is pretty that's close to 7? 6. So why don't I break this up into an x to the 6th and a loser x all by himself? Awesome loser, awesome loser. What about this guy? Is 12 divided by 3 something clean? Okay, so we'll just let the y to the 12th chill. So I see 3 things buried in here that I can simplify. All 3 of those, the 27, the x to the 6th, and the y to the 12th, can all be written as something cubed. That's so ridiculous. Okay, so let's go. Here we go. What can we clean? We can clean this. The cubic root of 27 is 3. The cubic root of x to the 6th, when you divide it, 6 divided by 3 is 2, right? So x to the 2nd. And with the y's, 12 divided by 3 is 4, right? So I'd have a y to the 4th. Now that's the things that were pretty. The leftover jerks, they're just left over under a root. I can't simplify them. There's nothing I can do. So the only thing that was left that wasn't pretty was the 2 and the x. So our final answer is this, plus or minus 3x squared y to the 4th, and the leftover chunk of square root of 2x, not square root, cube root. Okay, good. Number 2, not really any worse, same ideas. We have a negative in front of the root. I don't really care about that. I'm just trying to clean up the root, so the negative will just come for the ride. 16, a to the 5th, and a b to the 99th. Ooh. That's a big number. It's time to freak out. Donner party time. Yeah. When you get desperate, you eat each other. I don't know.
Oh yeah.
Yeah, Donner party. Donner party. Yeah. Donner. Did I say Dahmer? Well, I didn't mean to. He did. He did. He did. I guess if your last name starts with Donner or Dahmer, you're going to eat people. All right, here we go. Negative. Right off the bat. Square root of 16. That's something? Square root of 16 is not 2. It's 4, isn't it? Now, this is an even root, right? So I should be thinking about putting things in absolute values. Do you need to put 4 in absolute value? No, because 4 is already positive. So 4 from the 16. Now let's try to do it all in our mind. Ready? 5 divided by 2 ain't going to work, is it? But would you agree 4 divided by 2 works? Okay, so I'm going to break this into 2 parts. 4 A's and then a leftover A. Would you agree? Right off the bat, I'm going to make a leftover pile. There's 1 A left over, correct? For the A to the 4th, 4 divided by 2 is 2, right? So there's an A squared left. Do I need an absolute value around something squared? No. Squaring something, raise it to the 4th power, any even power will automatically already be positive, so we're good on that. Same logic on the B's. I don't think 99 divided by 2 is pretty either, right? But I think 98, 2 goes to 98, would you agree? So let's break it up into 98 B's and 1 B that's just a freak left over. And what is 98 divided by 2? 49. So that would turn to a B to the 49. Do I need an absolute value around things raised to odd powers? Yes, you do. So absolute value of b to the 49. And lastly, the c. 4 divided by 2 is pretty, right? So c squared, again, it's squared, so it's already positive, so I don't need an absolute value around that thing. So there's my final answer. It doesn't have to be written in that order. Okay. All right. And that's all there is, number 2. Repeat, repeat, repeat. Number 3. Let's see what's going on with that. They're not so bad. 3. Oh, no! Totally new problem. You should know what a 1/4 as an exponent means. It means it's a root, a 4th root. So in a roundabout way, their problem is the same as the other ones, the 4th root of this stuff, 625, x to the 4th, y to the 8th, and a z, right? All right, here we go. I hope they gave me 625 for a good reason. Do you have your table? 5. Okay. All right, so here we go. 4th root of this is 5. Don't need the absolute value because 5 is already positive, right? Okay, what about the x to the 4th? Is 4 divided by 4 something? It's 1. Now, x to the 1st, or x, could it be positive? Could it be negative? Could be either one. So I dang well better put it in absolute values for this one. I'm seeing a y squared next. You see a y squared next? Okay, it's squared. It's already positive, right? So don't need an absolute value for that one. And the z one, 1 divided by 4 ain't pretty, is it? So it's just kind of a leftover. So we have a 4th root of z all left over in the end. And that's about as good as we can do. If you want to say z to the 1/4, that would work too. Because they mean the same thing, don't they? I like it. In fact, I'd say z to the 1/4. When you get up a little higher, you never write the root symbol anymore. You just always call it to the 4th or something like that. So that's great. If you want to get rid of your root symbols for the rest of your life, I will have no problem with that. Lastly, number 4, 4th root. Now, don't freak out when the things are more complicated. It's the same logic. I have something to the 6th power inside of here, and I also have something to the 7th. Well, just because this is a plus b doesn't mean it's any different. 6 divided by 4, is that pretty? No. So what could you break this up to? A 4, right? And the leftover 2. Would you agree with that? Okay. Now, let's keep track of things. The leftover was a 2. So there's going to be a plus b to the 2nd leftover. This one's got 4, and 4 divided by 4 is 1, correct? So it's just going to be this thing to the 1st. But whenever you raise to an odd power, you definitely need an absolute value. So a plus b to the 1st, or just a plus b.
I'm totally confused. Where did the 4 come from?
We broke this into 2 parts. An a plus b to the 4th and an a plus b squared.
Okay.
This guy's a jerk. He's left over. This guy, nice and clean, right? Cool. Now just a y. Well, 7 divided by 4 is not pretty either, right? So could you break this into a 4 and a 3? And the 4 divided by 4 is again a 1, which I need to have in absolute values because it's not raised to an even power. And the 3 that were left over, well, they're just left over, so we'll put them in my leftover pile. And we're done. That's all there is to ever know about simplifying any root that might ever come your way the rest of your life. So it sucks, but it's powerful. Good skill to have. Good skill to have. And I know the absolute value thing is kind of a technicality. Don't sweat that too much if that's getting you. All right. Graphs of roots today. It's fun. It ain't so bad. No, I know it's going to be bad for you when it's not. Today won't be that bad for you. Yeah, all right. I'm tired. Go, go, go all day. Well, when it gets too slippery, if I park too close, there's this little. Yeah, and I've had my tire get stuck in that in years past, so I'm smarter now.
Okay, learn does not start with a T.
No, it does not. All right, here's your new homework. Take a second, jot this down, please. 6-3 due today, the root stuff. 6-4 is entirely about graphs, okay? This might be one you actually want to do online. It's very visual, and they'll have multiple choice and things like that, so I would encourage that. But of course, paper is always good too. 1 through 23, period. No odds, no evens, no other sections, just 1 through 23. 23. Our math is exquisite. If you're doing numbers 1 through 23, you're doing 23 problems.
Yes, I know.
Do you?
You understand what
No, I don't think I do. Yes. All of them. I always just post all of them in the whole section. So I don't know. Could be 50 or however many they got, but you only do 1 through 23. That's a point. Just 1 point. You're all fired. Okay, here we go. Section 6.4 is the title today, graphing radical functions. It's going to be exciting. All right. So I'm going to go off script for some of the basics. First thing they're going to talk about is even roots. So let's talk about even roots. The title of this is even roots. You can write that down as I play with things. Are you serious? Even roots. Okay. You should already know what a square root looks like. I hope you know it looks like this, half of a parabola by now. We know that? We should. That's a square root, correct? Yes, I am. I'm going to find a good one. This is going to be it. This is it. Ready? That's pretty good. We'll live with that one. Just like all even polynomials, x squared, x to the fourth, x to the sixth, x to the eighth, they all look the same. For the same reason, all the roots look the same. So a fourth root or a sixth root or an eighth root or any even root will always look like this every single time. And that's dying on me. Fresh one. Okay. Probably not. Yeah. All right. Very important to note, yes, any even root will look exactly like this. Of course, it could be shifted and moved around. We got to talk about that too. But that's your parent thing right there. Very important to know the domain and the range for these, because they're not what you usually write. You should already know by now you can't put negatives under square roots, right? Because they turn I-ish, right? Imaginary stuff. Same is true for a fourth root or a sixth root. Any even root, if you try to plug a negative in, it'll yell at you and say it's imaginary. We don't want to deal with that. Can you plug 0 in, though? Is the square root of 0 something? What is it? It's 0. The fourth root of 0 is 0. 0 is okay. Anything from 0 on is okay, including 0. So for once, your domains and ranges will have brackets on them this time because you can include that endpoint. I'm going to give a name to that endpoint. I'm just making it up. I'm not sure this is what it's really called. Vertex. Ted. The reason I'm going to call this the vertex is because this is half of a parabola, and this bottom part would be called the vertex. The range is not negative ever, but it is 0, and it goes all the way up to infinity. So their domain and ranges are the same by default. They give you a root. You will have the same thing. So your graph should look like that. And your domain should always be from 0 to infinity. And your range should always be 0 to infinity, unless we scooted or shipped it, right? All right. Now, what else they got to talk about besides that basic thing? Stretches and shifts. So let me go off script again, and we'll talk about stretches and shifts. I'm so sick of talking about this in my career. I can't. It's my job. If you take any root or any function, in our case a root, and you multiply by something, what does that do? That's a vertical stretch when you multiply. And if it happens to be negative, that's a vertical reflection. It ain't frozen over here. Oh, well, what the hell is
You said if it's negative, it's a reflection.
If it's a negative in front, the whole thing will reflect. Yeah. Okay. Well, what else could you do to your x's? You can shift some stuff. Let's get the easy one over with. What if you put something on the end? What's that do?
That's a horizontal stretch.
No. When you do it to the whole function, it's a vertical thing. And when you add, it's a vertical shift right there. Yeah, it just literally adds something to every value, so it just goes up by a certain amount. And of course, that's if you do it to the whole function, right? If you do things to the x's, then that's horizontal stuff. So if you take your x's times something, times is always about stretches. It's a horizontal stretch, or reflection if it's negative. And don't forget that horizontals are backwards. I'll try to give you some cheat sheets later so you'll even think about this stuff. Of course, you could also add something to your x. If you add something to your x, and that's whenever you add, it's about shifts. So horizontal shift, which is again backwards. It's all backwards all the time. Okay, sounds good to me. Let's see an example of this now. We'll pretend the projector's on. Here would be your first example. F of x equals the square root of 2x minus 6 and then a plus 1 on the outside.
The high school girls basketball team will still be playing at Burlington tonight as scheduled, and the girls can be dismissed at this time. Girls basketball team can be dismissed at this time. The boys basketball team at Burlington has been postponed until tomorrow. High school boys will have a shoot-around in the KB gym after school. High school boys will have a shoot-around in the KB gym after school.
All right. Now I have one other note to give you before we tackle this thing, okay? Jot this down. I'm going to try to cut through all the nonsense for you, all right? Instead of having to think about shifts and stretches and stuff like that. There's one thing that'll help your life quite a bit. And here's your note. If you need to know where this vertex is, like back and forth this way, here's how you know. The x coordinate of your vertex is where the stuff under the root, only the stuff under the root, equals the magic number 0. That's a biggie. It can help you take the thought out of, okay, there's a stretch and then there's a shift, and it's a little confusing. So I'll just try to cut through all the nonsense. That reference point is going to be where the stuff under the root equals 0. So let's take a look at that right off the bat. This example, let's look at the stuff under the root. Stuff under the root is just 2x minus 6, right? So we're going to try to figure out that's 0. And it's pretty obvious if you move the 6 over and divide by the 2, that happens at x equals 3. So there's your quick way to know that over at 1, 2, 3, that is where my vertex is going to be. However, that just tells you the horizontal story. The vertical story, how much you move it up and down, is of course based off of what the number on the end is, right? The number on the end is your vertical shift up and down. So if it's got a plus 1 on the end, that means it's going to be moved up 1. So right there is where my vertex is going to be. 3, 1. You get the x stuff from looking under the root, and you get the y stuff by whatever's on the end. Questions over that? Make sense? No? Yes? No? Okay. Well, now we just got to draw the darn thing. So does it look like that, or were there any reflections going on? I don't see a negative for my function, do you? I don't see a negative for my x's, do you? So there's no reflections. So it's going to look exactly like that. So it's just going to start here and go up. There's my graph. This is your rough sketch of this function. And we should also practice doing the domain and range. It's not going to be 0 to infinity because I shifted things. Yes, it will. Domain is going to be everything from 3, including it on. And the range, can you tell me what the range is? Nope. 1 to infinity. And we're all done with that problem. Okay. So this little starred note I have for you takes all the thought out of it for you. Figure out when the stuff under the root is equal to 0. And if you can do that, then you know exactly where it is going to be x-wise. That's going to be just fine. All right, here's your second example, -3 root x plus 1. Let's write that down. Now, right away, I see a negative. Can anybody tell me what that negative in front of the function is? What kind, vertical or horizontal? Vertical, right. So I am going to take this in my mind right off the bat and think that this thing is not going to open upwards, but kind of downwards like that. So just as a mental note, here's kind of what I'm thinking of as a template. That's exactly right. Here's the stuff under the root. You can probably spot that 0 at -1. Would you agree? So over here at -1, that's where my vertex will be. But are there any vertical shifts up and down? Yes, 2. So it's going to start up here at -1, 2. That's where my vertex is going to be. And we said there was a reflection, and it opens down, so it's going to open kind of down like that right there. You're pretty much done. This one opens down because of the reflection.
How come it doesn't go this way?
It's exactly like this, just flipped over the axis.
Okay.
Literally the same shape, flipped over, kind of goes down like that. Domain and range, anybody? What's the domain? -1 to infinity. Make sure you're always putting a bracket on the one that's not infinity, because this point does exist. I don't want you to lose points because you're just so used to putting parentheses all the time. The range, just like you go left to right, always go bottom to top, -infinity up to and including 2. So -infinity to 2 with a bracket right there. And there's the little green thing. Does it look like ours? Their green thing looks like mine. I'm pretty happy with that. Okay, now, last one about roots. And they do have some things about inequalities on this. Now, you've done this to death. Should this be a solid or dashed line? Look at the y. Y is less than? Dashed, right? And how do you shade when y is less than something? Below. So this example really is not a big stretch, and doing inequalities of this is not a big stretch at this point. The hard part's going to be getting the shape of the graph in the first place. So let's see what this thing looks like. I'm not even going to worry about the stupid, don't look at the picture, it's the answer. Let's see what we can do with this thing. Well, do you see any reflections? Do you see any negatives? I don't. So it's going to look exactly like this picture. Would you agree? Just moved around a little bit. How do I figure out the x? I set this equal to 0. It's a little complicated. I can't just see that one. So I'm going to set up an equation. Move the 5 over. Divide by 2. And you get -5/2, which is about -2.5. Not about, exactly. You see any number on the end? So I don't think it's going to move up and down at all, right? So it's just going to be over here at -5/2, which is about halfway between -2 and -3. Didn't move up and down. And I'm just going to draw it up here, but I'm not going to draw it solid because y is less than. So they put a whole bunch of dash things on this because it actually doesn't equal it. Another thing on that picture you might have noticed that I didn't do, it's gone now. They did not use a closed circle. They used a, and the reason for that's the same reason as the dash line. It doesn't actually be that line, does it? So it doesn't actually be that point either. This entire thing, it's just a boundary. It's going to be shaded below, right? Y is less than. So that means shade below. So literally you just shade below it and you're all done. Do not shade over here, because how can you say below it when it doesn't exist, right? Any questions over the inequality?
So X should be an open circle.
Because it's dash.
divided by half.
Yep, because it's dash. Yep. And if I had changed this problem and I put a equals, what would be the difference? A solid line and a solid circle, right? But I'd shade, and if it said y is greater than, you'd shade above. So the same old things we've been doing all year long with that kind of inequality junk. All right, that's it for even roots. Part 2, odd roots, right? Now this is not going to be that hard. In fact, it's a little easier, honestly. And I won't go through the theory of stretches and shifts and all that stuff again, because it's really the same thing. So last topic today, odd roots. This is something you haven't seen before. We graph square roots all year long, or we're exposed to them, so that's something. But here's what an odd root looks like. It kind of comes up, it goes straight up for just a split second, and then off like that. Ish. It always will go through the origin, unless, of course, there's a shift or all that stuff. That's what we're going to talk about. Yeah. These are actually pretty easy because they exist everywhere. This exists from negative infinity to infinity. And it does very slowly creep all the way up and down. So your range is also negative infinity to infinity. So no matter what shifts you do, or stretches, or reflections, it's still going to cover everything from negative infinity to infinity. So whatever odd root you do, this is always your domain and range, no matter what. You don't have to think about it, okay? Odd root, boom, there it is. Well, that's what a cubic root looks like, and a fifth root, and a seventh root. And any odd root kind of looks like this. And here's your note to how to deal with moving around odd things. It's going to be the same exact note as the even degrees. We move the vertex around there, correct? Well, this isn't really a vertex anymore, is it? I'll give it a name. I'll call it the center. I'm making that up. Call it Bob if you feel. I don't care. But the same logic's going to apply. The x-coordinate of your center is where the stuff under the root again equals 0. It's the same exact note you just wrote down, just not with the word vertex, with the word center. And again, that will help guide you in figuring out what these graphs are going to look like. Other than that exact same nonsense. So let's look at a particular example. Let's try this one out. P of x is the cubic root of x plus 5. All right, here we go. Shape. Do you see any negatives floating around? I don't see one here. I don't see one there. No reflection, so it's going to look exactly like this. Maybe just scooted some. Well, how do you find out where the center is going to be? You set the stuff under the root equal to 0. Well, the stuff under the root is x plus 5. And I think we could all agree that's 0 when x is negative 5, right? So over here at 1, 2, 3, 4, 5, negative 5, that's where my center will be. There's no numbers on the outside, right? Nothing here, right? So no moving up and down. So the center is going to be literally right there. And it's the same shape. We didn't have any reflections or anything. So we just kind of draw a nice little curvy thing, have it come up and go straight up for just a split second, and then go off. It doesn't have to be perfect. Something like that. And without even thinking about it, what's the domain and range? Negative infinity, yeah, for everything. Yep. Don't have to think about it for an odd root at all. It's a really crappy drawing I did. Oh, that side's all pretty, and this one's like some weird thing. I don't know. I don't like that. All right. Let's try this one. Last one, I think. So this is the cubic root again of 4 minus x. It's a little bit wonky. Q? Oh, I guessed right. +1. Thank you. Now, the first thing I noticed is they put the stuff in the root in a weird order. Would you concur? And if they ever write something in a weird order, they're just screwing with you. Put them in the right order and then look at fresh. So this one right here, I'd rather call it negative x plus 4 than the other way around because that's kind of annoying. Okay. Well, right off the bat, let's talk about shapes. Do you see any reflections? I see a reflection this time. There's a negative. It's not in front of the whole function. It's in front of the x. And x stuffs are horizontals, correct? So I expect this thing to be shifted, or excuse me, reflected horizontally. So this piece over here will now open up like this, fair? And this piece will now open up like that. So in my mind, I'm kind of expecting to look kind of like that-ish. Does that look like a reflection horizontally? Does to me. Now the question is just, where do I draw the dang center? Well, it's 4 this time. And don't be afraid to go sit down and write an equation and set equal to 0. That's why we have equations. If you move the x over, then yeah, x is 4. There's a +1 on the end. What's that do to any graph? Shifts it up 1. So I expect my center to be at 4, 1, 2, 3, 4, and 1 up. There will be my center for this root graph. And we said it kind of got reflected, so it looks like this, correct? So we're just going to fill in the gaps now. Kind of comes in, goes down, straight down for just a split second, levels off. Something like this would be a graph of that particular root. And that's about it. I don't think there's any other examples. You guys got any questions?
Can you type these into your calculator to see what they look like?
Yes, you can. Go to math real quick. Everybody, get your calculator out. Hit the math button on the left. Use this to check your brain, not to do your work. This is how we get problems over the years. If you go to math and you go down a little bit, there is something that says this, like a x with a root. You see that? Yeah, click that. And when you do, there will be boxes to fill in.
I still haven't found the math box. Sorry.
It's way over on the left,
On the left.
like a few down, yeah.
Okay, there we go.
Hit math. If you scroll down, you should see this symbol. And if you select it, then it should give you something like this to enter things in. Clearly up in the top, you put the root, and down here you put whatever the hell the root is. Cool? Okay. Use that to check yourself. Check yourself. But you got your calculators, you got your brains, and you got all the normal visual crap they give you. So you should be more than fine on this assignment. And that concludes today. 6-3 is due. 6-4, we will have work time for tomorrow. But you do have a good 15 minutes now, so don't screw around and do nothing. Get a good start on 6-4 if you need.
So no work day tomorrow.
There is a work day tomorrow, but let's not waste 15 minutes now.